So let's go ahead now and continue with some more examples. These examples we're about to talk about from the EX8 example in my Java 8 folder in my GitHub repository are getting into more sophisticated uses of things like completion stage methods and arbitrary-arity methods and exception handling methods. What we've looked at in first part of this walkthrough were really things that were the basic features. So they're cool, but they're not really why you would use CompletableFuture. So let's now transition into that discussion. So the first thing we're going to do is we're going to create ourselves a random number generator, and then we're going to go ahead and use CompletableFuture supply async to make ourselves a random big fraction. You've probably seen this make big fraction factor method before. I use it all the time in my examples because it comes in very handy. And all it does is it makes a gigantic big integer as the numerator, and then a much smaller big integer, random big integer as the denominator. And then it combines the numerator and denominator to make a big fraction, which is either reduced or non-reduced depending on the parameter that's passed to it. And in this case, we're passing in true, and we're passing in true because this is going to run in a background thread. And in that background thread, we're going to make this gigantic big fraction, and then we're going to multiply it by this constant, which is called big reduced fraction, which you can see up here, which is also reduced. And so we're going to create one random big fraction and multiply it. And then we're going to create a second random big fraction and multiply it. And both of those operations are going to take place in the background in a thread in the common fork join pool. And then down here, we're going to apply several very interesting completion stage methods, and we're going to use them in conjunction with this local variable called mixed fraction printer, which is just going to print the results. And you can see what we do here is we take CompletableFuture 1, which was the first big fraction that's being created and reduced, created in a reduced form and multiplied. And then we take CF2, which is the second big fraction that's being created, reduced, and multiplied in the background. And we wait until they're both done. And then we combine the results by adding them together with the big fraction bifunction. And after we do that, then the last thing we do is we print the results using the mixed fraction printer. So this is showing off a very cool completion stage method called then combine, which waits for both of two previous asynchronous results to complete. And then when that's done, it triggers the then except completion stage method, which will go ahead and do the side effect that's designated in that consumer and then return CompletableFuture to void. So that's a really cool example of kind of forking and joining computations using CompletableFuture features like supply async and then combine. All right, so that's the first of the cool completion stage methods. Now let's go ahead and take a look at something that is called the exception handling methods. And this is going to show the use of the handle exception handling method. And this is a really fun example. So the first thing we're going to do is we're going to make a stream, and the stream will first contain true, and the stream will then contain false. And if we come in here and throw exception is true, then we're going to make a denominator that's 0. Otherwise, we're going to make a denominator that's 1. And I think you already see where this is headed. Obviously, if we have a denominator that's 0, and we go ahead and we make ourselves a big fraction with the 0 denominator, whether we do this synchronously or asynchronously, it's going to throw the arithmetic exception, as it should. And of course, we don't want our program to come to a screeching halt. So what we're going to do instead is we're going to use the handle exception handling method. And what this will do is it takes two parameters. One is the fraction if all went well, if we got a valid fraction as a result of doing this big fraction value of factory method. Or if we had denominator 0, we're going to get the exception. And fraction and exception are mutually exclusive. They can't both be null. They can't both be non-null. So if the fraction is null, that means that we had an exception, in which case we get the exception name, which would basically be divide by 0. I mean, arithmetic exception divide by 0. And then we're just going to return 0 as the result, just so we don't blow up. Just say it. If you try to divide by 0, it's a 0. Maybe not the best result, but it's a result. Otherwise, we got a fraction that was non-null. So in that case, we can multiply it by this big reduced fraction. So if an exception occurs, we take this path through handle. If an exception does not occur, we take that path through handle. In either case, in one case, if it's an exception, we indicate what went wrong. We return 0. So we always return a valid value, and handle will swallow the exception. It will have handled it, if you will. And then when we're done, we go ahead and print the results, which will either be the multiplication of the big fraction by the reduced big fraction, or it'll be 0. Okay, so what we're going to do here, notice we're making this stream. So we have stream of true, stream of false. We use map, so we're either going to get the results of multiplying that or a 0. And that's going to come in as a stream of completable future to void. And then what we're going to do is we're going to collect the results into a single completable future that will trigger when both completable futures complete. And remember, they're both running in the background. So let's go ahead and take a look at what toFuture is. So toFuture is a factory method that creates an instance of something called a futures collector. You can see that toFuture creates a futures collector. So what indeed is futures collector? Let me just go ahead and make that type safe. So futures collector is a Java collector. What is a Java collector, you ask? Well, we've talked about Java collector before in the context of the streams framework, and it's basically a class that will convert a stream of something into something else. In this case, the futures collector will create a stream of completable future objects to objects of type T into a single completable future that will be triggered to return a list of items of type T when all the futures in the stream have completed, all the completable futures have completed. So let's take a look at how this works. So here is futures collector. It's a generic type. It implements the collector interface. So it works on a stream of completable futures of type T. It will use an accumulator, which is a list of completable futures of type T to accumulate each element in the stream. And it will finish with a completable future to a list of elements of type T. So when all the elements in the stream have been accumulated and they've all finished, we're going to end up with a single completable future, which when completed, when triggered, will then return a list of the items that have finished their computations asynchronously. So this is like absolutely the coolest thing ever. And let's take a look at how this works. So we go ahead and make ourselves a supplier, and the supplier will basically a factory that returns a constructor reference that'll make a new array list. We then have an accumulator, and the accumulator, as you can see, is going to return a by consumer that will add an element of completable future of type T to the list of completable future to type T that we created using the supplier up here. So this is what makes the accumulator, which is called the mutable result container. And this will add the next item to it. Very simple, very concise. Were we to use parallel streams, which we are not going to use here, but were we to use them, here's the combiner that takes two partial lists of completable futures to type T and adds another to the end of one and returns one. So it basically combines them. We're not using that here, but we have to provide it for completeness. And then finally, we've got the real meat of this whole thing, which is the finisher method. And this is what is going to transform the mutable result container's contents into the final result. And this is just absolutely the coolest thing ever. It's described in the videos, but I just want to walk through because it's a little bit complicated and I want to make sure you're comfortable and understand what it's doing because it's really handy. And you'll be using a variant of this in programming assignment number 4. So what we do is what this thing is passed is the mutable result container, which in this case is a list or an array list of completable futures of type T. So that's what futures is. It's a list. We take this list and we convert it to an array of completable futures of type T. And the reason we do that is because the all of method, for mysterious reasons that I never have fully understood, doesn't work on a list, it works on an array or a varargs parameter. Who knows why? The long and the short of it is we have to convert the list to an array. So we do that. All of returns a single completable future that will be triggered when all the asynchronous computations associated with this list / array of completable futures are all done. So after we've accumulated all the completable futures in the stream into our mutable result container, we then are going to use all of to get back a single completable future that will wait for all those completable futures to be done. And when that happens, the then apply completion stage method will be triggered, which will go ahead and take the original list of completable futures, convert it to a stream of completable futures, and then join each of those completable futures to type T to make a stream of objects of type T. And the thing to note here is that this join call, or these join calls, because there'll be multiple join calls, one per element in the futures list, will never block. And the reason it'll never block is because we never would have gotten here in the first place if the completable future return from all of hadn't completed. And it's only going to complete when all of the other completable futures are done. So this call will just never block. It'll just convert from a completable future of T to an object of T. And then all we do is we collect the results into a list. So we're going to get back a list of objects of type T. And that is what comes back from then apply. And then apply, of course, will wrap that as a completable future to a list of objects of type T. And so that's what we get back from this particular collector. So what we're doing, and this is a very long and roundabout way of explaining all this, if you take a look here, we use collect, which will take that collector that was created by the toFuture factor method, and we'll get back a completable future to a list of void. And when we're all done, when everything is finished, we're going to use the then compose method basically as a finalizer, and we're going to print the results. That just says when everything is finished, print the results. And then we return the fact that we're done. And we do that as a way to avoid nesting. So that's a really, really, really cool little example. Test fraction exceptions 1 is super cool. And let's go see what it looks like. If you take a look at test fraction exceptions 1, you can see that it did indeed get an arithmetic exception. Divide by 0, fraction denominator is 0. And so we got back 0 and 450, the 0 being the stuff that obviously was the exception arm through this particular code. That shows a lot of really, really cool features. Here's another example, which is doing similar things. This is called test fraction exceptions 2. It's going to do the same thing, more or less, except it's going to use the exception handling method as opposed to using the handle exception handling method. So again, we have a stream of true, false. We use map to create ourselves a non-zero and a 0 denominator. We go ahead and create ourselves the big fraction. The first time through, it'll throw an exception, of course. If it throws an exception, control is automatically transferred to the exceptionally method here, which will go ahead and basically print the error message or append the error message and then return 0. If an exception is not thrown, in contrast, control transfers to the then apply method, which will multiply the fraction by the big reduced fraction. So either then apply gets called if there's no exception and exceptionally is skipped, or if there's an exception, then apply is skipped and exceptionally is called. In either case, when we're all done with that, exceptionally swallows the exception, and then we go ahead and call then except to print the results. As before, we use collect and then compose, just like we had shown earlier. Here's yet another way to do exception handling, and this is going to demonstrate the when complete method. So overall is the same. We've got a stream of true and false Booleans. We map things to either be a big fraction that'll throw an exception or one that won't. In this particular case, we use when complete. And when complete is this very interesting method. It's kind of like the peak method on Java streams, where it is only used for side effects. It does not affect the results in any way, shape, or form. But what we do here is if we get a fraction that's non-null, then an exception was not thrown, so we print the results or append the results we want printed. However, if fraction was null, in other words, if EX was not null, that means we got an exception. So we go ahead and we append the exception method. And then we're going to swallow the exception and just return whatever the exception happened to be. If there was an exception, we're going to just return 0. So for my money, probably handle is the cleanest of these things because it kind of consolidates when complete and exceptionally. It's a little bit cleaner, but you can see how you can apply all these different techniques in a common way. All right, and the rest of the method is the same. Just got a couple more things to look at here. We're going to take a look at an interesting method called test fraction multiplications 1. And this is going to go ahead and make a lambda function to asynchronously reduce and multiply a big fraction. You can see what it does. We call reduce and multiply fraction. It creates a completable future that will reduce the unreduced fraction in the background. It'll then use the then compose method to go ahead and call supply async to multiply the reduced fraction with the big reduced fraction constant. And we use then compose here because we don't want to have nested. We don't want to have nesting. If we don't use then compose and instead we were to use then apply, then the return value here would be incorrect. And we'd have to make this completable future to completable future of big fraction. So it would just be, more verbose. So we don't want to do that. So instead, we're going to use then compose instead of then apply. Then what we do, once we've got this variable, this function variable defined here as a lambda, we're going to generate an infinite stream of random big fractions that are unreduced. We're going to limit the number of big fractions generated to be S max fraction, which is 10. And then we're going to use the reduce and multiply fraction variable to go ahead and reduce and multiply all those fractions asynchronously. So keep in mind that we're going to do all the reduction and all the multiplication asynchronously in the background using these threads. And that's going to generate a stream of completable futures to big fractions. And then with all those things running in the background, we're going to collect them using our futures collector to get a completable future to a list of those big fractions. And when all that is done, we're then going to use the then compose completion stage method to take that single completable future when it's done, which will yield a list, and we're going to call the sort and print list method. And this sort and print list method is just the coolest thing ever. So what it does is it creates two completable futures which use two different sorting algorithms, quicksort and heapsort. So we quicksort and heapsort that list in parallel using completable future supply async. So quicksort will be running in one thread in the worker thread pool, the common fork join pool. Heapsort will be running in a different worker thread in the common fork join pool. And then we're going to use another completion stage method called except either, which will say whichever one finishes first, quicksort or heapsort, take whichever one came first, take the sorted list and print the results and display the results. So that's another really good example of how you can use completion stage methods, in this case, the logical OR variant, to take whichever one happens to finish first, which is just so cool. So that's that example. And then I think we got just a couple more examples. This demonstrates all these same ideas, except that rather than using nested supply async calls, which is what we've done before. If you take a look at what we've done before, we had supply async, then compose, supply async, which is certainly doable, but it's a little bit unwieldy. Instead, we replace that with supply async, and then we use then apply async. And then apply async will run the registered action here, which was going to multiply the reduced fraction by the S big reduced fraction. It'll run it in another thread in the common fork join pool. So it's a little bit cleaner because we don't have to have then compose and supply async kind of nested together. So I really like that approach better. And then down here, we do the same thing we did before. We generate an infinite stream. We limit the stream to 10 random big fractions. We reduce and multiply them. We use our collector to get back a single completable future that waits for all those computations to be done. And then we go ahead and sort and print the list in parallel. And I think that might be it. This is the make big fraction method. Here's sort and print list. And that looks pretty, oh, and here's quicksort, which goes ahead and makes an array list that wraps this thing up. And we use quicksort, and then we also have Heapsort, which is, I have an implementation of Heapsort that I wrote. And I think we probably actually, we don't need to make a copy here. I don't think there's any particular reason we have to make a copy. We could probably just sort the list. But maybe the more I think about it, we probably can't do that because that'll interfere because we'll be sorting the same list twice. So anyway, that is that particular example. And if you take a look at the results here, you can see that we get some pretty gigantic big fractions. They go on and on and on because these are gigantic big fractions with enormous amounts of precision. And yet it all works and things get sorted correctly and it sorts in the proper order using the big fraction class's equal method to do the sorting correctly.